name is Willem Hendricks, but Damian and I would say friends. We talk a lot about AI, machine learning, where it can go wrong. It's always interesting. So I will try to put some of the discussions I have with him in the presentation. And I will. What's your name? Laura. I will also address this because this is something that we also discussed. So let's start right there. This is a little bit how you could say the steps of AI, of how we use computers. Because statistics, summarized, is maybe the first thing that we teach to computers. And this has to do with AI. What was about the first thing that a computer can do? What was it?
Compute.
Compute, and what could it compute? Indeed, a simple a summation of a few numbers. And this was the very first thing that computers were able to do. They could sum numbers. So you gave them 1 and 2 and 3, and it could do 1 plus 2 plus 3, 6. This is the first thing. But it was fantastic because it can do it very fast and a lot of skills. So then suddenly it's handy to use it for administration. The first processors couldn't actually multiply. It was just, well, let's just do a lot of additions. 6 times 8 is just 6 plus 6 plus 6 plus 6. And later we were able to teach computers how to multiply. So this is something that we know how it works. And we told the computer, this is a procedure, you do it. Then later we did data mining, and then we repeat and automated these tasks. For instance, we told the computer what is the mean of the number and what is the variation. But at some point we had a problem. For instance, can you tell me what this object is? I think it's correct. But we were struggling quite some years to teach computers this because we know it, we were able to do it, but we cannot explain what goes on in our brain, how this works. And this is the paradox, I think it's Polanyi who named this as a paradox. We humans are capable of much, much more than we can explain. And recognizing a plant is one of them. It's very easy for us. You need to tell your child 1 or 2 times, and he's always will know what's a plant. But if you give them a pencil and tell, give me the rules, what's the difference between plant and fruit, it becomes very difficult. If you say something green that comes out of the ground, then maybe the Hulk is also a plant. So no, that doesn't work. And you can keep adding rules, but it doesn't work. The machine will make mistakes. So then we have, luckily, machine learning. We give the computer, we give them some freedom and learn from your own mistakes, a little bit of feedback, and then over time the computer, you could say, creates its own rules to learn what is a plant. And here I think is a little bit the problem with explainability, because if we were so good that we could understand the whole process, we were able to write down the rules, and this is what makes a good candidate. So it should have this much year of experience, but if we don't know these rules and we need machine learning to understand it, how can we expect then back that the machine learning can explain to us how these rules are? Because our brain was not good enough to come up with the first place. So this is, I think, a little bit a paradox in explainability. It's a little bit like, all right, there's something difficult. We humans have no idea how it works, so we need machine learning to understand it. And then we come up with, yes, it should be explainable, so please explain me all how this process works. I think it's a little bit, at some point it always be a paradox. If our brain is not big enough to understand those complex systems, the models that we train to understand them might never be able to explain themselves to us. And if it was so, maybe we were able to write down it in the first place. So this is not really a thing in AI that this is a little bit my own view, Polanyi's paradox. So we are able to do much more than we can explain. So therefore we need machines to understand it. And here I feel there's a little bit of paradox. How can we then demand of the systems, now you explain it to me, I'm just a little human brain, so AI is going further and further. So this is what I think is really interesting. And also, if you see what computers are able to do with machine learning, it goes a little bit in steps of what we can explain. So indeed, summation, multiplication is something very easy to explain, so that computers can do those the first time. It's a little bit more difficult to explain the rules of grammar, so spell check came later. It's far more difficult to explain how something looks, what makes a cat and a dog different. And there's still a lot on the list. For instance, love. Who can explain love? Anybody can here explain love to me, please? No? So I guess this is on the end of the list of what computers might be able to do. And also empathy and consciousness, if it even is the thing, those are difficult. So I guess they are at the end of the list, and that's also here, at the end of the list, artificial intelligence, reasoning, because we don't know how it is, so then it's very difficult to make a computer do it. So really interesting, keeps also my mind explainability, and even with, when we sometimes have discussions with government entities, all the models should be explainable. Well, that's maybe that's a few steps ahead, I believe. I think it would already be really, really nice if we document the data, what went in, what features, and document what went out. That would already be fantastic. And then later we can talk about things like explainability. This is a funny comic that Damian found, maybe popped up in your LinkedIn feed sometimes. It's about, oh my god, fairness. First we didn't have thought about, and then oh crap. And I think the oh crap is literally the examples that Dasha gave. There's already examples in real life that just went wrong. People literally stayed longer in jail because of a model. So the oh crap is indeed done, and now we're suddenly busy. So maybe this graph looks a little bit like the explainability of your Google Trends, so then this is something, but it's only a few steps where it can go wrong. And here are some aspects of where we might need to views how we need to check our models. And the first one, is it fair? Thank you, you already covered that one. So is it easy to understand? Explainability? Well, maybe we cannot explain the full model, but Shed and Lime, there's tools to explain or at least get some feeling for a single decision. So that is the best we got so far. Hopefully we'll make some progress. Did anyone tamper with it? This is also a very fun one. Robustness. The Tesla, welcome. There's still, in the front there's still seats. The Tesla car is automatic self-driving. Let me get some hands. Who thinks it's possible to design a sticker that looks black? For us it would just look like a black sticker. Who thinks it's possible to design a sticker that I can put on the ground and the Tesla car will suddenly change lane because it will confuse him? Who thinks this is possible? From everybody, who thinks this already happened? Yes, indeed, you're right, this already happened. So this is robustness. And again, like the explainability, I don't know if it's, again, possible to demand from AI, you should be 100% robust, you should not possible to fool with. Because again, we humans are very easy to fool. There's even professional foolers, they are called magicians. So we go to the show, please fool me, we give them money, please fool me. No, oh, I don't know how you do it. But then AI, no, you're not allowed to be fooled, because there's kids on the road with flashlights, and then if they shine in my eyes, oh, whoa, maybe I have an accident. So yeah, of course, the AI also has weak spots. They're a little bit difficult to spot, but of course they can be fooled. So here, I indeed think it's an important area, but again here, I think we need to be sensible. We can make them more robust, but there always will be a weak spot. And just like it's not allowed to stand on the A4 and with a flashlight try to make drivers a little bit, how to say, the eyes difficult to see. Yeah, how's it called? White blindness, bright blindness. That's not allowed. The police will try you. So it should also not be allowed to place stickers on the floor to make all the Tesla drivers go well. It's not that AI is wrong. It's just humans can be fooled by magicians. Well, AI can also be fooled, except they call hackers or I don't know, AI for business. Maybe there's a new name because every few months there's a new name in AI space. I see, oh, there's a job, an AI conscious CEO, but there's always a name. So maybe there should be a name for this. The last one, is it accountable? This is a little bit boring. Yeah, the data, what happened with the data. But this is the one where I, in practice, is maybe the one we encounter the most. Is this the pizza hall? Oh, okay. Oh. Let me know when the pizza is there, because I'm also hungry. So, is it accountable? Here is the examples are really a lot. I guess if you ever have scrolled through some data, for sure you must have seen that if the data is gathered over the years or months, that there's sudden changes that has nothing to do with that the process changed, but that maybe there was a new law, a new rule that defined what is good or bad. For instance, the Dutch NS, they were very creative with the rule, when is a train late? Well, if we cancel a train, it's not late anymore. And when you see the trains late, suddenly there's a drop in the data. That has nothing to do with that they were better, there was a change. A more recent example, the coronavirus, that is now in the newspapers every day. If you would look at the people that got infected, suddenly you see a spike. This was also just by data lineage. There was a new definition, and I'm not sure what happened there, but what I do know is that the person responsible for defining what is when somebody is infected was changed, and the new guy was more strict. So how could that have an effect if you create a model that was predicting the number of patients in the next month, and because this little change of the positions in the Chinese infection prevention something, there was a huge spike. So these are all things that can happen. Go back to, there's one thing that I missed that I forgot to say. We talked a lot about machine learning. Can I hear some popular models? What are typical machine learning models? Anyone was fine, guys.
Random forest.
Random forest, thank you. Another one? Which one? The classifier? What? BS?
Naive Bayes.
Naive Bayes, and another one? XGBoost, thank you. So we had Naive Bayes, XGBoost, Random Forest, and
That's the one. Bayes classic.
okay. So two of those are tree-based. The Random Forest, we make a tree. The XGBoost is almost similar like the Random Forest. It's a tree, but in the Random Forest, the second tree is just random. In the XGBoost, the tree is going to make the previous tree a little bit better. So we make a lot of trees randomly or try to improve the previous one. How does a tree work? It's actually fantastic. The basic thing that makes the most popular models, if you could see Kaggle, which is a data science competition, and just by my little 4-point survey in this room, the Random Forest and XGBoost are popular. It's the most discriminating thing we have on Earth, because we designed it to be very, very discriminating. How does a tree work? For instance, you need to predict if somebody is going to buy a certain product, and we have consumer data, and it goes into the tree, and the tree needs to make a decision. It literally tries to discriminate. Let me see, age. Can I find people with 12-year node, 30 node, 20, 24? This is good. People below 24 like it, and after, I'm going to keep that in mind. let me see if I can discriminate on sex, males, females, pretty good, but no, not as good as age. And it will try to discriminate as good as it can. And when it finally has found the most discriminating feature, for instance age, it will say, good, this is my first branch of the tree. So this is the funny, we talk about fairness and everything, and the most popular machine learning model, I thought this is literally a discriminator, but it, you know, so there's a funny thing that we need to fix. We create a discriminator, but not just one. We're going to create 500 of them, because with the XGBoost, the first one needs to even discriminate more than the previous one. So that is what we started with machine learning, and now we need to have some fixing to do. Oh crap! So that's a little bit yeah, that's a little bit what we're busy with. All right. So we want it to be fair. This is a wrong way of thinking. For instance, in the resume example, if I simply delete the field that the name, then I'm probably done, and it won't discriminate on, for instance, sex, male, female. Well, that's not true, because there are proxies. So those are other things in the data that actually might reveal if you're male or female. Such like the example was the type of university you went, but it can be much more subtle. For this example, I searched, is it possible to find the sex of a person just based on the text he or she wrote? In 1999, we were already able to do this with, I think, 90% accuracy. So that was the previous century. So I guess right now we can do it much, much better. So by removing the thing that we are most scared about, we actually make it worse. I don't know the details of the resume technique, but it might be that with the best intentions, they try to remove everything that could reveal if somebody is a guy, he or she, but then by all other things that you cannot possibly think of, the model find out anyway that if you use these kind of sentences, maybe guys use shorter sentences, something like that, and then it found out anyway, and still, because of our bad history, we just amplify it with AI instead of make it fair. So, this is another example of it. This is maybe the most racist picture that human ever created. It is something like a map where the neighborhoods in Brooklyn were colored by how well you were likely to pay. So, and this is something related to also a way to have a proxy in your data. Your postal code might hide a lot of things that you don't want to. So if you say, no, it's all right, we don't know the age of the person. Do you have the postal code? Yes. Well, it could be that in this neighborhood there's a lot of young people starting their family. In that neighborhood there's the old 80 plus living there the final years of their life in a nice hill. So the postal code is usually a very strong proxy for all kinds of things that you haven't thought about. And this is a little bit a message from, don't do the quick fix. It's alright, I removed the age from my data, it's completely fair. No, what you did is, you put yourself blindsided, because now you're completely lost. Please keep it in the data, then at least we can detect it. If we remove it, who knows, the model will find proxies, because again, the discriminating trees might be really creative and still find out what's going on. So this is a demo of our AI Fairness 360. I will later show some examples of this. This is a screenshot, and what it actually is, it is a start. It is not the answer to fairness. It is an open source toolkit that IBM put on the internet with some tooling that could help you to, for instance, make a model more robust, or explain a few things, or well, all the things about bias mitigation, and there's a few funny examples. One of them about robustness is I really like. I talked about magicians earlier. I will do a magic trick and make an AI think a cat is an ambulance or something. Maybe you've seen it before, but that is in the toolkit that is working there. And yeah, so let's take a look at a few of those. I have Wi-Fi, I think I have. Let me check. Yeah. Oh, Domino's has delayed. Their pizzas will be later. Because I have a tendency to talk too long. Do we want a little break right now, or should we continue?
We could stop at 6, break 15 minutes, 10 minutes, drinks, and wait for the pizza, so continue in 45 minutes.
Please ask the audience.
So we could stop in 15 minutes. I think that would be a natural break, get some refreshments, and then wait for the pizzas to arrive, grab the pizza, and start somewhere at 6:45. Is that okay with you?
Okay. All right.
Okay.
Yep. I have internet. I always use mute, you know. So let's do first the magic trick. This is a web interface to show you the basics of making a model more robust. But if you like, developer.ibm.com, we have a lot of developer codes, examples, things you can do, and there. If you like to later code a little bit yourself and see all the little bits and bytes of this example, there is a notebook example where you go step by step to make a giant panda into a cappuccino. Maybe is that the coffee? So there is some. If you like to see the code behind this, you can do it. And there's a lot of more nice examples here. But here I'm going to show you the basics of make a model more robust. So again, what are we busy with here? A model can predict something, usually with images. Is it a cat or a dog? And we're going to try to fool him. Just like we're able to fool ourselves, we can fool AI, which is not necessarily bad. It's just at least something we should be aware of. And then if we know how it works, maybe we can do something about it. So let's take an image. This is cheese, and right now you see the original image, and here simulate attack. Here I can select a attack, and that means I can. This is a little bit like changing the pixels a little bit here and there. This pixel a little bit more red. This pixel a little bit more green. And if you do that smarter, you confuse the model, and that is because the most popular family in how this works in deep learning are convolutional neural networks, CNN. And those networks are, they work fantastic, but their working is a little bit like the following. We take an image, and then a convolutional neural network will create usually 8 or 60 more images of the original images, and these you could say are new colors, new kind of features of the original image. So for this cheese image, object detection, usually there's a new color that is telling where are more pointy things. There's another color that maybe says, is there a lot of yellow in this area? There's another color. So if a computer doesn't see an image like us, it sees maybe 100 or 1,000 different colors that all might have some interpretation that we have, but not. And then based on all the let's say 1,000 colors that it has created magically by itself, it will simply use them all and see, oh, this must be a human, because I see a little bit round things that could be a nose. I see a lot of hairy in color 860. Whoa, there's also some weird organic shapes, that must be the ear. Something nosy in the image, something eerie, and also some hair. I'm 99% sure this is a human. That is how image recognition works, a little bit like this. And because it works like this, it's very easy to fool. For instance, if you create a human where the eyes are at the ears and the ears are at the eyes, of course, those feature planes will still be the same. It will still see some eye stuff and some ear stuff, and it will say, 99% sure this is a human. If I show it to my child, he would probably laugh and say, what is that? That is totally wrong. Well, AI doesn't. So you can a little bit fool an image by putting very little, some nosy shape, a little bit here, you won't detect it, but little bit by little, the nosy color of the convolutional starts to get a little bit more prominent. And if I also make the hairy color a little bit more prominent, then suddenly, and it's undetectable, but enough to fool the network. So this is, in mathematics you call this hand waving, it's not really an explanation. This is a little bit in big step how it works, how we can fool image recognition. So we need an attack. This is the fast gradient method, and here I can put the intensity of the attack. If I do none, the original and the modified image will look 100% the same. So I increase it a little bit by medium. Suddenly, the network thinks this is a wallet. It's not a cheese thing anymore. But, well, you can see a slight difference. You can see there is some weird magic pixel thingy going on. So this is still visible for us, but let's take a more sophisticated attack. Let's take the cappuccino, for instance. And now I do the C and W attack. Don't ask me what it is, I have no idea. It's a better attack. So I'm going to put it on high. And here my eyes cannot see the difference anymore. For me, it's the original pixel. So this attack is really subtle. Only a few pixels are changed, but enough for this model to think this is a jellyfish with a very high certainty. This is what happens. And this is what happened with the sticker that fooled the Tesla. When I saw this the first time, I thought, yeah, that's very theoretical. You need probably access to the training and the model to do such an attack. This is not that dangerous. This is research attacks, nothing real. But the attacks get better and better. You don't need the source code of the model anymore, and the stickers from the Tesla are a proof of this. We can make them already, put them on the road. So it's not just digital. What I'm meaning to say is feeding the exact digital image of to the model in your computer works, but also print it out, make a photo, and then feed it to the model also works. So it's not enough to just put a camera between. So what can we do about this? Well, literally like evolution, we can make it a little bit more difficult by put some noise on the training data. And now, just by adding some noise, so this is literally throwing digital dirt at the training data, it has difficulty already to do the attack. It's less sure than, oh here, good, than the original, but it now at least is not fooled anymore. And sometimes throwing some digital dirt on the training data will also improve the accuracy of your model. So if we have to be fair, we have to make a little bit of balance, but for robustness, sometimes it has a positive effect. So by making models a little bit more tougher, by making the training data a little bit some dirt on it, the models becomes better. So there's other. Well, you can play with this. So the URL is in the slide deck, and I think it's shared, so everybody can play with this. I think I'm not that much an expert of facial recognition. What I do know is that the earlier generation of facial recognition would simply take, I think, about 40 or so points in your face. So let's take this point of my eye, that point also at the other side, and the corners of my mouth, and all kinds of points, and then simply do something with the distance and proportions of each of those points. And that was the first generation of facial recognition, not necessarily deep learning yet, but the proportion, the length of all your 40 or so markers was enough to find you in a million people. So that's pretty amazing. So maybe you can fool it by take some duct tape and stretch your mouth a little bit. I wouldn't be surprised if it gets fooled like that. There is an example of stickers that you can put on your T-shirt that will fool the network totally. I saw two guys on YouTube or LinkedIn that did something like this. So I would try the duct tape first because I think it's very fun. But there's also some weird QR code-alike sticker that will fool the whole network as a whole. So it's certainly possible to fool. What I'm not sure, and that's interesting, could it be that you go to buy some makeup and do very subtle things on your face that will fool the network, but the guy at the airport still thinks, oh, yeah, I saw him last week. Nice, welcome back, sir. And then you don't have duct tape on your face, and that I'm not sure. That I really would like to know. Is there anybody who knows this?
I have a news